Good evening and welcome to you all. I'm Luc Vinet. I'm the director of the CRM. And I will say a few words in French. So, tout d'abord, chère Catherine, mes félicitations, toutes mes félicitations. C'est d'autant plus approprié que je parle en français, en l'occurrence. Et je le rappelais, il me semble que c'était hier qu'avec Jerry Marsden, on créait ce prix CRM-Fields à l'époque, auquel s'est associé le PIMS après sa création. Et avec le temps, je pense que ce prix des instituts est devenu l'un des plus grands honneurs que la communauté canadienne mathématique décerne. On dit ça évidemment en étant un peu fier de nous, mais je le crois quand même. Et en l'occurrence, ce prix est très, très mérité. Alors, toutes mes félicitations à toi, Catherine. La conférence de ce soir témoigne de la collaboration des instituts à plusieurs égards et aussi à leur facilité d'adaptation à les circonstances. Alors, je vous remercie toutes et tous de votre présence, de vous joindre à nous ce soir. Et je vous souhaite une excellente soirée en compagnie de Catherine, qui pourrait évidemment nous éblouir par son jeu pianistique, mais qui le fera tout autant en nous montrant comment elle peut subjuguer les vagues scélérates. C'est comme ça qu'on dit rogue waves en français, vagues scélérates. Alors, bonne soirée à tous. Encore une fois, bravo Catherine.
Thank you, Luke. My name is Kumar Murthy. I'm the director of the Fields Institute. And let me add my words of welcome to those of Luke on behalf of the Fields Institute. Welcome. I was going to say to this evening's program, but I hope in this new Zoom world that we have people maybe from other time zones and other parts of the world. So good day to you wherever you are. I hope wherever you're staying safe and healthy. Fields Institute is younger than the Centre de Recherche Mathématique, but has taken a role in the Canadian mathematical scene and in the international mathematical scene in promoting the entire spectrum of mathematical sciences research and training. We have thematic programs, and this term, in fact, the thematic program at the Institute is on mathematical hydrodynamics. So it's particularly appropriate that the special lecture this evening is about ocean waves. This prize, the CRM-Fields-PIMS prize, is a joint initiative of the three institutes, as you can see. It's meant to recognize research achievements in the mathematical sciences, which have been primarily conducted in Canada or in affiliation to a Canadian university. I think really we need more prizes of this kind, more recognition to express our commitment to promoting excellence in mathematics in Canada and in the world. Both at the junior and the more established level of established researchers. So this is a really good thing for us, and we should have more of it. Hearty congratulations to this year's winner, my colleague at the University of Toronto, Professor Catherine Sulem. I'm really looking forward to her lectures, which I'm sure will be inspiring and informational. Once again, welcome to this evening's program, and I'll pass the floor now to Jim Colliander, who's director of the Pacific Institute of Mathematical Sciences. Jim.
Thank you very much. Hello, everyone. I'm Jim Colliander. I'm the director of the Pacific Institute for the Mathematical Sciences. It's my great honor to introduce Professor Catherine Sulem. Catherine Sulem is an outstanding mathematician who has made foundational contributions in a wide variety of evolution equations. She's made contributions in nonlinear Schrödinger equations, in the understanding of water waves, in the understanding of fluid equations more generally. She's also studied kinetic equations. She's contributed advances in the understanding of the behavior of solutions. She's answered the most important question in this subject, which is what happens. Sometimes she has provided definitive answers. She's provided insights into the formation of singularities. She's given insights into the behavior of coherent solutions called solitons. And she's also developed insights into phenomena called turbulence. Catherine Sulem uses a variety of methods in these studies, not just rigorous mathematical analysis. She also combines that with numerical methods to generate a variety of insights. She's studied integrable and non-integrable systems and has made foundational contributions throughout her career. Beyond her own research contributions, she's also contributed to building the capacity of mathematics in Canada and beyond. Through her scholarship, she has written a definitive text on the nonlinear Schrödinger equation with her brother that has provided a pathway to introduce many others into the subject. And she's also mentored many students, postdocs, and colleagues. And I am personally very grateful to Catherine for the mentorship that she provided to me when I was a young assistant professor at the University of Toronto. Catherine Sulem, I look forward to your talk. Congratulations on winning this year's CRM-Fields-PIMS prize.
Well, thank you very much, Kumar, Jim, and Luc, for your very kind words and generous introduction. I am very honored to have been awarded this prize, the CRM-Fields-PIMS prize, and I would like to warmly thank the Institute for this award. I have participated to many wonderful programs at the three institutes, CRM, Fields, and PIMS, and I would like to thank the Institute for their continued support of to the entire international mathematical community. And I'm also very grateful to my collaborators who have played a vital role in my research, and I would like to thank them for their friendship and also for their inspiration. Thank you. So today I will talk about dynamics of ocean waves. And so waves in the ocean are very important in all aspects of our life. Ocean covers over 70% of the surface of the Earth, and about 40% of the world's population live within 100 kilometers of the coast of the estuaries. So the study of waves has a continued relevance to our lives, to the importance of the sea in our civilization. It has numerous applications, of course, that include coastal engineering, ocean wave prediction, global scale phenomenon, such as oceanic circulation and currents, for example, the Gulf Stream or El Nino. It has also applications to sub-mesoscale motion, which concerns scales of order 1 to 10 kilometers that are associated to strong vertical velocities. This motion have important effect on air-sea transfer, on distribution of nutrients near the surface, and also on the growth of marine plants. There are many kinds of waves. There are many kinds of waves in the oceans. In normal situations, surface water waves are generated by the wind. Particles of water are moved from their positions by the wind and then return to the original position by gravity. It is a process of transfer of energy from wind to water, and wind waves range for small size, small ripples, to huge waves. There are other kinds of water waves. They include extreme waves. So the extreme waves, there are of several types. The tsunamis, that we all remember the tsunamis in Indian Ocean and in Chile, in Japan. They are triggered by powerful earthquakes inside the ocean. There are extreme waves generated by hurricanes. And there are also extreme waves that we call rogue waves, or freak waves, or monster waves. And these waves, they are not well understood. They are large spontaneous waves rising up out of moderate sea, and they disappearing very fast, so it's very hard to measure them or even to reproduce them in a laboratory. In this this picture is represents what's called the Dropner wave, or also the New Year's wave. It was the first rogue wave that happened to be detected by a measurement instrument, and it happened on that evening of 1995 at the Dropner platform on the North Sea. And this picture shows us the height of the waves, essentially 5 meters, and suddenly a giant one of almost 20 meters. It is believed that it was a real wave, and minor damage was inflicted on the platform, which confirmed the validity of the reading made by laser sensor. There are also another type of wave that I will discuss later. These include the internal waves. So internal waves, they propagate inside the oceans at the interface between internal layers of different densities. Often these different densities are related to sharp gradient of temperature, for example, in tropical seas, or sharp gradient of salinities. An example is Detroit of Gibraltar, where the Atlantic Ocean meets the Mediterranean. So they are generated, for example, by tides that cause water to move over bottom topography, and then the cold water from the bottom is pushed from over the ridge and set a disturbance. So in general, they are not directly visible to the observer, but they have influence on measurements of currents, undersea navigation, and submerged construction. And they also play an important role in mixing layers of water in the ocean. So here is a kind of description of various types of ocean waves. I will start essentially this presentation by historic notes. Many aspects of mathematical analysis were motivated by the study of fluid mechanics and waves in particular, and in turn, hydrodynamics is a source of challenging problems at the heart of nonlinear analysis. I will mention here a book by Olivier Darrigol, who is a historian of science, and the title of the book is Worlds of Flows, a history of hydrodynamics from the Bernoullis to Prant. And he starts his book by a beautiful quotation of a letter from Thomson to Stokes in 1857 that says, I think hydrodynamics is to be the roots of all physical science and is at present second to none in the beauty of its mathematics. This book, Words of Flow, well, the fact that words is the plural refers to the fact that there were essentially 2 words. On one hand, the theoreticians, they included mathematicians, which at the time were called geometers, included geometers, philosophers, and on the other hand, there was the applied science. The other word was the applied scientist, who worked on hydraulics, naval architecture, engineering projects. And what is quite fascinating is how the author also addresses the social and professional aspect of these 2 words. And of course, he also shows the influence of the great scientists such as Navier, Stokes, Rayleigh, Helmholtz, who brought these two worlds closer for many aspects of the fluids. So it was a quite inspiring book. Then I will talk about, I will present the water wave problem, and especially the governing equation that describe the motion of a free surface. For example, the waves at the surface of ocean. And the water wave problem is a very classical problem that has remarkable properties that various asymptotics lead to various canonical equations of mathematical physics, such as the Korteweg-de-Vries equation, the nonlinear Schrödinger equation, and many others. And due to the complexity of the dynamics and the diversity of the phenomena, it has been often necessary to combine different approaches, mathematical analysis, asymptotics, high precision numerical simulations, comparison with experiment. So in the third part of my talk, I will illustrate this approach on the problem of interaction of internal waves and surface waves, in particular the effect of these internal waves on surface waves. And this is a work I did some time ago with Walter Craig and Philippe Guyenne. So Walter Craig, many of you have known him. He was a professor and Canada research chair at McMaster University. And he was a leading expert on hydrodynamics and water waves. He sadly passed away in January 2019. And of course, it was very sad. He was my longtime collaborator and very close friend. So it was very sad for me, but I keep wonderful memories of our collaborations. So now I will start with the first part, which is historical notes. So these slides summarize or at least list the great names of the 18th centuries, starting with Newton, who was essentially who proposed the first mathematical theory of waves, in particular the approximate theory for small amplitude waves, which what we call now the linear theory. Then I'm presenting the Bernoullis. There is the father Johann and the son Daniel. There is another Bernoulli, Jacob, which was he was famous for his work on the probability theory. So Daniel Bernoulli is often associated to conservation of energy and balance of forces. D'Alembert was a mathematician. He was a physicist. He was also a music theorist. He was a reviewer of a memoir written by Rameau and submitted to the Academy about the principle of harmony. And D'Alembert is really associated to the foundation of the hydrodynamic laws. He wrote several books, several memoirs on winds, on fluid resistance. And his name is also associated to what we call the D'Alembert paradox. So it corresponds to a certain contradiction reached by D'Alembert, which says essentially that if one considers the motion of a fluid along a straight long tube with constant velocity, and inside this fluid, a stationary object, a fixed object, then the force exerted by the flow on the object is zero. So that was not really intuitively correct. So that was a surprising result. And this contradiction was later solved by Stokes, who introduced the notion of viscosity. And it was even better understood later by the discovery and the description of boundary layers by Prandtl in the beginning of the 20th century. Euler, who gave the name to the Euler equations, he established the fundamental equation of motions for the incompressible fluid, in particular the balance of forces exerted on a particle of fluid at position x and time t. I also mentioned the work of Lagrange and the Mémoire sur la théorie du mouvement des fluides. This memoir contains a full second part dedicated to the water wave problem, and in particular what we call potential flows. So potential flows are flows that are such that the velocity can be written as a gradient of potential, and it plays a very important role in the study of water waves. We will see that a little bit later. So this was the 18th century. The 19th century brought new notions. It brought the notion of viscosity, of vorticity, and also of notion of stability and instability. So viscosity was introduced by Navier, and he invented it by analogy with molecular theory of elasticity that he also invented. So viscosity measures the fluid resistance to the flow. It corresponds somehow to the thickness of the fluid. If honey is very viscous, but water is not viscous. Also, the notion of vorticity was introduced. So in the Lagrange memoir that I mentioned, he concentrated on potential flows, and this potential flow, as I said, is a situation where the velocity is the gradient of the function phi, the velocity potential. Helmholtz, he pointed out to the importance of vorticity, which measures the local spinning of the fluid and is defined by omega is the curl of U. Helmholtz was also very much interested in acoustics, and he was fascinated by the physics of tones and the foundation of music. And he went to mathematics from acoustic. So here is a picture of Kelvin-Helmholtz, what we call Kelvin-Helmholtz instability. This picture represents waves, wave clouds taken in Australia. And there are two different layers of air moving at different speeds. The upper layer moves faster and roll over, and this instability refers to the Kelvin-Helmholtz instability. It's a situation where the incompressibility of the fluid imposes that the normal component of the velocity fluid is the same on both sides, but the tangent, there is a jump in the tangential velocity, and the jump is measures the density of the vorticity. So in this situation, the vorticity is concentrated on sheet, and it's a delta function on sheet. There is also the notion of vortex filaments. So in that case, the vorticity is concentrated on curves. And I will conclude this history with the discovery of the soliton. So this discovery really spanned a period of 140 years from this 34 to the 70s. And it started with the observation of a Scottish engineer, Scott Russell, who observed a soliton, who observed the great wave of translation. He called it the great wave of translation, which is a wave of permanent form propagating at constant speed. So here, this picture, we see a soliton in the ocean. Well, it is moving towards us, towards the coast. At this stage of the discovery of Russell, the question was really to establish the existence of such waves, in particular their resilience or their stability. So Airy, he argued that a linear theory cannot produce waves of permanent form. And it was only 30 years later that Boussinesq and Rayleigh, they provided a nonlinear theory that gave rise to a solitary wave, and they obtained that theory by approximating the water wave problem in a certain regime. And this is how they derived what we today call the Boussinesq system or the Korteweg-de Vries equation. And then nothing really happened until 1955, where Fermi, Pascal, Ulam, the three physicists, were exploring heat conductivity in solids. And they were asking the question about whether thermalization process happens, which means does equipartition of energy occurs. And so they had a discrete model of a one-dimensional discrete model, and they were having a numerical simulations. And to their surprise, they did not observe thermalization. And it was a question really what was exactly the process. And what happened is that they observed that the energy that was initially contained in the lower mode was flowing back and forth among several lower modes, but after a certain time was recollected to the lowest mode. And this observation stayed without explanation until Kruskal and Zabusky in '65 approached this problem from a continuous point of view, and they derived the Korteweg-de Vries equation as a universal model, and they found its solution in the form of solitons. So that was quite an extraordinary discovery, which was very soon followed by the discovery of inverse scattering by Green, Gardner, Kruskal, Miura, and later Zakharov, Shabbat, and the very rich mathematical properties of what now we call integrable systems. So tomorrow in my talk, I will talk about inverse scattering, and in particular recent advances in dispersive nonlinear PDEs that use the inverse scattering character of some important PDEs, some important integrable systems. So this concludes the historic part, and now I will move to the equations, so the water wave problem, and in particular the governing equations. So here's the general picture. We're going to assume that the fluid is filling a domain, fluid domain, that is defined like here, where x, y, x is the horizontal coordinate in R1 or R2, and y will be the vertical coordinate, And the fluid is all these points between where where x is in R1 or R2, and the vertical coordinates is between a bottom, that here the bottom is flat, is minus h, and eta, which refers to the surface elevation. It's a free surface, so it's in a general problem of a three-dimensional water waves. It's a surface. In many of the mathematical studies, people study either the two-dimensional water wave problem, which corresponds where this interface between water and air is a curve, or the three-dimensional water wave problem, where this interface is a surface. So today, because of the complexity of the problem, I will restrict myself to d equals 1, which means that x is in R. There is no dependence in the other transverse, direction, like a little bit like in this picture where nothing happens in the x2, let's say. And so this is the domain of the fluid. We assume that it is incompressible. That is translated in saying that the divergence of the velocity, u is the velocity, is 0. I will assume that it is a potential flow, that it is irrotational. That's a common hypothesis in oceanography, where people are interested in propagation of waves. Although there are many more recent work where the rotational, where the vorticity is included in the analysis. But today I will restrict myself to potential flows. And these two equations imply that inside the domain, the velocity potential, the function phi here, satisfied the Laplace equation. So it's a harmonic function. But it is a free boundary problem. The boundary between the air and the water is unknown. This is part of the unknown. So all the difficulty will be to describe really the movement of this interface. So what are the boundary conditions? Well, at the bottom of the domain, that's the bottom of the ocean, we will write the usual Euler boundary condition that claims that the normal component of the velocity, so in our case, the normal component is the derivative respect to the variable y of phi at minus h is 0. And the difficulty comes into describing the nonlinear boundary condition at the free surface. And there are two boundary conditions. One is called the kinematic conditions. It essentially says that the free surface moves according to the flow, and it translates into this relation between the time derivative of eta, which is the interface, the free surface, and the partial derivative of phi, the velocity potential, with respect to horizontal and vertical component. The second condition is called the dynamical condition, and it's called also the Bernoulli condition, because Bernoulli really studied the balances of force, and it expresses that in absence of wind and in absence of surface tension, the pressure on the interface is continuous. So the pressure is just equal to the atmospheric pressure. And this translates into this equation. G here is the acceleration of gravity due to the gravity. So the water wave system is the system composed of the Laplace equation in this unknown domain, a boundary condition on the bottom, and two boundary conditions on the top. Well, this over-determined system, or it's not over-determined because eta is unknown. So this is a system. It's very difficult to deal with, and there was a discovery in '68 by Zakharov, who discovered that the water wave system, once if one write it in a system of appropriate coordinates, is a Hamiltonian system. And this form of the water wave problem have been used quite intensively in many studies. So that's why I thought it would be nice to see how it comes into the picture. So the Hamiltonian under consideration is naturally the total energy, the sum of kinetic and potential. And it's possible to write it in terms of our unknown, the velocity potential and the interface, in the following way. The kinetic energy is the integration over the full domain, the fluid domains of 1/2 of the velocity, which also can be written as 1/2 of the gradient of the velocity potential. And the potential energy is measured by, again, the integral of the domain of g times the elevation y. And one can integrate the potential energy and discard the constant of integration. So the Hamiltonian is expressed in the sum of these two terms. Now, if we remember that phi is a harmonic function and we applied the Stokes Green's identity, the first term can be rewritten as phi times the Laplacian phi, which is 0, plus 1/2 of the product of phi and d phi dn at the free surface and the bottom. At the bottom it is 0, so what remains, this term is 0. The only thing that remains for the kinetic energy is a second term. And at this point, it is interesting to introduce the quantity that I have denoted xi here, which is the trace of the velocity potential on the surface. And if we denote by g of eta, the Dirichlet-Neumann operator associated to the domain, that we'll define in a minute, this kinetic energy identifies to an integral of xi, which is the phi here, the trace of phi on the surface, and d phi dn is going to be the Dirichlet to the Dirichlet phi dn is equal to g applied to xi. In other words, the normal derivative in terms of the Dirichlet data. I will explain that a little bit better here. The Dirichlet-Neumann operator is the operator to a Dirichlet data after solving the Laplace equation in the domain associate the normal derivatives. And in this situation, the Hamiltonian now can be expressed in terms of only two variables, the surface elevation and the trace of the velocity potential on the surface elevation. Oops, there are too many 1/2 here. 1/2 of g of xi g eta plus little g, which is a constant, the gravity, eta squared. So these two variables, eta and xi, are the canonical variable for the water wave problem written in the double coordinates. Oops, and the system, the water wave problem is now take the form of the evolution for eta and xi in terms of, in this form, in the form of a Hamiltonian system. Now, immediately we see calculating the derivative of h, or the variation of h in terms of the in terms of xi, is not complicated, is G applied to Xi, but calculating the variation of H with respect to eta involves the variation, the shape derivative of G, which is a non-trivial calculation. However, it's possible to do it. And now the wave systems take the form of this blue system here. The evolution for eta and Xi, both of them are a function of X and T with value in R. And it's a first order quasi-linear system. It's a complicated system which involves a non-local operator, the Dirichlet-Neumann operator. And this formulation has been used extensively for many questions, local and global well-posedness theory with many participants, Lange, Germain, Rasmussen, Chattard, Alazar Burkswili, Alazar Delors, Ionescu Puzeteri, for the very difficult question of global well-posedness. It has been used for derivation and validation of asymptotic models, with the book here of David Lange, proving the validity of these asymptotic models, and also in numerical simulations. So it has been quite useful. Now, as I said in the beginning, the water wave problem has the property of leading to important equation of mathematical physics in certain regime. And due to the complexity of the dynamics and the qualitative difference of the waves at different scales, it has been very important to consider different scaling regime and derive different approximate asymptotic equations. So the first simple approximation is, of course, to consider small amplitude solution. And in particular, small amplitude means that we linearize near water at rest. In that case, the system reduces to the one written here, where the derivative of eta is equal to the Dirichlet-Neumann operator for a flat domain, flat from the bottom and flat. The lid is flat and the bottom is flat. And what is G of 0? Well, it consists in solving the Laplace equation in this domain with specific boundary condition. It happens to be a Fourier multiplier that is really written here, D hyperbolic tangent HD. H is the depth, it's the depth of that channel. And in Fourier, it's solvable explicitly. One finds that eta is the superposition of Fourier modes of sinusoidal waves of the form exponential kx minus omega t, where omega and k are related by the dispersion relation. That's very important in dispersive problems. Now, in the example of small amplitude, but shallow water, that means then the wave, the equation for the surface wave is simply the linear wave equation propagating with velocity c square root of gh. G, I remind you, it's the gravity constant, and h is the depth. It's the depth. So it's the very classical calculation is to calculate the tsunami velocity and propagating in the open ocean. So if one takes the data from the tsunami of the 2004 in the Indian Ocean, the distance between two crests is 100 kilometers. The surface elevation of the waves in the open ocean is small, it's only 2 meters. And the depth of the ocean in different parts of the ocean, of Indian Ocean is 3-4 kilometers across the Bay of Bengal, and in the Andaman Sea, more like 2 kilometers. So if one calculates the velocity of this tsunami, one finds 650 kilometers or 500 kilometers per hour, which is extremely fast, corresponds to the velocity of a plane. So that's explained in the catastrophe that it produced. Now that was the linear situation. There are, of course, more sophisticated asymptotic regime, and to derive them, one needs to define 3 typical lengths in the domain. One is little h, represent the depth, wavelength, which is essentially the distance between 2 crests, and the amplitude of the wave. And from these 3 parameters, one built the parameter delta, which is the shallowness, and epsilon is the non-linearity. So one of the very famous regime is what's called small amplitude long waves, when these 2 parameters are small, but they are in a special relation, epsilon equals delta square. And then in this case, this is the approximation that Boussinesq and Rayleigh that I discussed earlier. It's in this approximation that they derived the Korteweg-de Vries equation. So in this variable, the psi represent moving waves with velocity c. It's a long waves, and time tau also represents a very long time dynamics. Another important regime that has many applications in oceanography is when one considers small amplitude solutions, no hypothesis on the depth, it can be deep water or shallow water, but one is interested in very long time and long distance dynamics. So in that case, the linear approximation is too rough. And Zakharov in '68, in this very short paper, when he derived the Hamiltonian character, also derived that an approximation consists in modulating a sinusoidal wave by a function a that is not, instead of having a constant, it is a slow varying function that evolves in this new variable according to the nonlinear Schrödinger equation. So the new time tau is a very long time. The new xi, the new position, is also long distance. It's moving with what we call the group velocity. Omega prime is a group velocity. And the dispersion is quite canonical. It always happens to be the second derivative of the dispersion. There are many other extension to 2D surface waves, extension to higher order approximation, to internal wave, to non-flat bottom. And it happens that many of these asymptotic models are Hamiltonian PDE and often also integrable systems. So I will discuss some tomorrow. Okay, so now I will go to the last problem, the last part, which concerns the problem of coupling between internal and surface wave in a stratified fluid. So here is general observations about coupling between internal and surface wave in a stratified fluid. So these internal waves, they occur within a fluid that is density stratified because of a sharp variation in temperature and salinity. They are not visible to the observer, but they have an influence on the surface waves. it was observed that internal waves are common features in many regions of the world. And the early measurements were due to Perry and Schmicker in the Andaman Sea, which is a part of the Indian Ocean, where they found group of internal waves up to 80 meters high and 2,000 meters long. On the main, so where they were situated? They were situated at the main thermocline, 500 meters in water of 500 meters deep. So I have a number of pictures that are, some are really spectacular, I must say. This one, so this is simple internal wave is signaled, it's materialized somehow by the sharp variation of temperature. So this is a picture I took from a paper, Internal Solitons in the Andaman Sea, published in Science by Osborne and Birch, famous oceanographers. These represent the isotherm contours, and this is somehow what materialized the internal waves. It's where the sharp gradient of isotherm. This is another picture I took from a paper by Duda, 2004, and this measures again the contours of the temperature in part of the South China Sea, and where we see the sharp gradient materialize in an internal wave. So this is a picture that was, that it is a photograph taken from the space shuttle, and there are many photographs in Atlas of Oceanic, of Office of Naval Research. So this is taken from the space shuttle, and we see some ripples. We believe that these ripples are induced by internal waves. So the image is taken under the highly incident light of the late afternoon. And the presence of this internal wave gives rise to this differential reflectancy. This picture is even more spectacular. So here we see, so there is a passage of internal waves that give rise to characteristic features on the surface in the form of narrow bands of rough waters. So they're called rips. And these rough waters are separated by large area of calm water. And in Osborne Birch book paper, they refer this calm water as mill pond. So somehow, from a fixed reference point at the sea surface, the passing soliton reflects the ambient sea waves in front of it, as if it was sweeping the sea state in front of it. That explains this narrow. And we're going to explain these narrow bands. We're going to explain the narrow bands and this large calm water. But I found that this picture is really extraordinary. And we see this long band extending on very large distance. This is 100 kilometers. So maybe I will skip these photographs because we don't have so much time. But I will simply mention Maury. Maury, he was an oceanographer, an astronomer, a naval officer, and he wrote many books. He traveled extensively, and he was also called the scientist of the sea. And in this book, Physical Geography of the Sea and its Meteorology, he describes this rip phenomena, and I will not read it very much, but clearly he says in most places rippling are thought to be produced by strong currents, but here they are frequently seen where there is no perceptible current. And he continues by saying these ripplings are seen in calm weather, approaching from a distance. In the night, their noise is heard a considerable time before they come near. They beat against the sides of the ship with great violence and pass on. A small boat can not always resist to the turbulence of these remarkable ripplings. That was written in 18 something. Okay, and there are many, of course, a lot of studies about internal waves. There is a small number of references, but in terms of the work of an applied mathematician, the question is to find a theoretical framework that models the observed phenomena, which is first derive a system of PDE in the physical relevant regime. One part of the work is really to follow the movements of the passing soliton and model. There is a resonant interaction of non-inner wave and internal, of the non-inner internal waves and the surface wave. The second part, well, once one introduce a system, analyze and interpret the observation, in particular understand the narrowness of the location of the rip, the smoothing of the surface, the mill point effect, and try to see whether this phenomenon coincide with realistic situation, which corresponds to small density difference between fluid layers and small depth ratio between the two layers of fluid. And what we observed in our work was an analogy with quantum mechanics, where the regime of parameters that under consideration in the realistic situations corresponds to semi-classical limit of the Schrödinger equation with a potential well. The potential well is going to be the internal soliton of depression and a small dispersion coefficient leading to a process analogous to radiative absorption. And we illustrate that with numerical simulation. So because time is running a little bit, I'm going to skip the mathematical model. It's really writing the water wave problem for two fluids. And I will jump to the system obtained, the asymptotic equation modeling the internal wave and the free surface. So the internal wave, after introducing appropriate scaling, is and a lot of calculations, is modeled by the Korteweg-de Vries equation, while the free surface is modeled by a linear Schrödinger equation. So linear because the amplitude of the surface wave is much smaller than the amplitude of the internal wave. So in a sense, the internal wave influence the surface wave, but the surface wave do not influence the internal wave. So the Korteweg-de Vries is, they are decoupled. And the parameters A and delta depend only on the physical parameters, H1 over H, the ratio of the two depths, and ρ1 over ρ, the density ratio. And they are given by explicit formula. The coupling between R and W, which is the modulated amplitude of the free surface, is through this term, which is the linear term in the Schrödinger equation, where R plays the role of a potential. And in realistic situation, ρ1 over ρ is 1, is close to 1, H1 over H is small. The KdV soliton appears as a wave of depression, like we saw in the pictures of the isotherm, a wave of depression, a soliton of depression, while in the Schrödinger equation, the parameter delta, after changing the coordinates in a frame of reference, moving with the soliton, becomes a stationary Schrödinger equation with a dispersion here extremely small. So this is a picture of delta square as a function of h1 over h for R1 for density ratio close to 1. So the red curve is below here. So because of this particular form of the Schrödinger equation, we're able to claim that it is analogous to semi-classical regime with a large but finite number of eigenvalues, bound states highly localized near the minimum of the potential well. And this is a calculation of the system that represent associated to parameter of the Oregon coast. So that was numbers that we took from a paper by Bakanov and Ostrovsky for ratio of density very close to 1, ratio of h over h, which is relatively small, a very small amplitude. And it's interesting to see that the surface wavelength corresponding to the parameters in this setting is 25 centimeters, consistent with observation of the surface ripple. So this is a sketch of the in the physical variable, but the vertical scale has been exaggerated. Otherwise, we would not have seen it. So I will finish the talk by stating a couple of results concerning the interpretation. The first result concerns a lower bound of that measures the absorption of energy into the bound state as the internal wave propagates in the ambient C state. We prove that there is an interval of wave numbers such that in the limit delta, there was a dispersion relation, tend to 0, there is a lower bound for this quantity. Somehow the wave energy from the surface, from the sea surface, is trapped by the bound state during the internal wave passage. And this gives rise to the phenomenon of the rip. The second result coming from the analysis concerns the continuous spectrum, wave planes that at plus and minus infinity takes the following form. So we have an incident wave, which is this one, that reflects. A part of it reflects and a part of it is transmitted. In the regime under consideration, the coefficient B, the reflection coefficient, and the transmission coefficient are asymptotic to -1 and 0. So in the reference, the interpretation of this observation is that in the reference frame of the internal soliton, entering the background C state, quasi-monochromatic surface waves are absorbed into the rip as bound state, or else they are effectively reflected in front of it. So the fact that very little of the surface wave is transmitted through the soliton gives rise to this very calm sea behind the advancing soliton that was described as a Mill-Pond effect. And I will just take 1 minute to discuss perspective and open problems. So of course, this analysis was restricted to 1 KdV soliton. It would be richer to assume more general solution like N soliton solutions. In that case, the analysis would be more difficult because it would not be a time-independent Schrödinger equation. The three-dimensional case is much richer. We had a partial study giving rise to an internal wave satisfying the Kadomtsev-Pechvili equation, which is the extension of the Korteweg-de Vries equation to the 2D problem. Also, the 3D case is much richer, has a much richer complex dynamics because it has very large classes of exact traveling solutions. And I think I will stop here. That was an example where we used different approaches to try to understand or describe the physical phenomenon. And yeah, I thank you very much for your attention. Thank you.
Well, thank you, Catherine, for a very beautiful talk and that description of how you could get the rip and the mill pond effect was really very satisfying. I wonder if you could very quickly go back to that picture you had of the rip and the mill pond effect and just
yes, that was that picture. That was this one.
That one, yes.
So these are the long rip extending to long.
Which way are the waves moving?
So you have to imagine. So that's a picture from the above,
right? And
soliton is coming, let's say, from the, I don't know if the image
left, right?
From the left, and it creates. So this is below this one. There is one soliton, and then a certain time later, there was another internal wave creating this rip, this narrow band of rock water, and that it is another soliton, another internal wave moving to the left, moving from left to right, and this is the ambient sea. So if you want, there is this picture that I haven't seen, as I've shown, but this is sitting in a boat, and this is at the horizon. We see the breaking line of waves, I mean the breaking waves, a line of breaking waves, and it comes in closer and closer to the boat. So at this place, at this time, the sea is essentially 0.6 meters, and then it comes closer to the boat because it's moving towards this boat. The vessel is, then the weights are 1.8 meters. Then, the rip is receding because it's passing the boat. And after a little while, the rip has completely disappeared. The waves, the sea is dropped to ripples of 1 meter.
Right.
So that was also taken from this very beautiful article that was happening in the 80s, where somehow these two oceanographers discusses this use of internal waves, internal soliton.
Right. Okay, thank you. So I think we have some time for some questions. I don't have a way to control this, so if people just pose their questions, but maybe you could turn on your video when you ask a question so we can see the speaker at that point.
Right. Could I ask a question?
François?
Yes. So, merci beaucoup, Catherine. C'était un plaisir de t'entendre, évidemment, comme toujours. J'aurais bien aimé qu'on fasse ça en personne, je veux dire, plutôt que par COVID.
Moi aussi.
On se serait fait au moins un bisou, ça aurait été chouette. Okay, I'll switch to English to ask my two questions. So these are very simple questions. The first one is I know the answer. So your Hamiltonian system is obviously hyperbolic. I mean, you just have to see all the h in your trigonometric functions. And yeah. we all know, yes, we all know that meteorology and oceans obey hyperbolic equations in the sense of Asymptotic. So it's not elliptic, it's not parabolic, it's really hyperbolic and chaotic. So, so I think I've answered my own question. But the second question is, then I really want an answer because I have no idea of that. You said in the part 2 of your talk that the Hamiltonian was integrable. So this means that you have R3 here, R3. So the cotangent space is R6, and then you need 2. So you need 2 aside. I mean, in addition to the Hamiltonian function, you need 2 momenta. Okay, you need 2 momenta. What are these 2 momenta?
First of all, it depends what you mean by integrable system. I did not say the water wave is an integrable system. It is not an integrable system. It's a Hamiltonian system. Well, integrable depends how you.
It's just the Kolmogorov-Arnold-Moser notion of integrable. It means, or it goes back to Lagrange, if you wish.
Okay.
It has to be two other momenta.
Well, there is the conservation of
Poisson commute, which are Hamiltonian, and then you're
of mass.
Then you're on a torus, and then you can solve the equation by Jacobi equations.
Okay, so conservation of mass and conservation of momentum. There are two other conservation of two other conserved quantities.
Okay, conservation of mass, I understand. But what is the conservation of momentum? Are you talking about the angular momentum?
Yes, it's defined as integral of the velocity, derivative of c respect to x multiplied by eta.
Okay, this is your angular momentum.
So there are these 2 quantities, yeah.
Okay.
Well, I was thinking integrable system in the sense of inverse scattering because tomorrow I'm going to talk about inverse scattering.
Okay, that's for tomorrow. That's for tomorrow. Okay, thank you.
Okay, we have a question from Olivier Lafitte.
Bonjour, Catherine. Hello. I have a question when the bottom is not fixed. That means when h depends on x. Do you know of any results or any theories, not only in shallow waters, but in any case?
Yes, well, in fact, the importance, the influence of the bottom topography on the surface waves is a very much studied subject, and people have really asked the question, how does it influence the asymptotic models? For example, how does it influence the derivation of the Korteweg-de Vries equation, or how does it influence the shallow water limit? And depending on the scales, it may have an important effect.
So that could be in David Land's book, or where could we find it?
Oh yes, well, there are many, of course, David Land book. I have myself several papers with Walter Craig on the influence of the bottom to the surface wave.
Mm-hmm.
In different settings, you may, sometimes if the bottom is very rough, you can use homogenization. If it is very smooth, then it has limited influence on the interface. And there are some scaling regime where it is important to consider, to take into account this influence. And in mathematically, rough bottom can be modeled either by, the simplest case is to assume that it is periodic, okay. But people have also assumed that it is described by a random process, random process. Yes, there are many. Well, if you leave me your email, I could send you a number of references.
I'll send you an email. Thank you very much.
Okay, I think we have a question from Manu Paranjapi.
Yes. So I was intrigued by your analysis of the tsunami waves, which went at 500 kilometers per hour. My question was, why didn't they dissipate over they seem to have gone thousands of kilometers? Yes. How does dissipation affect?
There was very little dissipation, and so of course this analysis is done in the open sea. It doesn't take into account, I mean, the coastal, the fact that suddenly the coast, it arrived to the coast. So this is the very simple calculation. Calculating the propagation, the velocity of the propagation, and it's of course it stops its validity. The validity is limited to the open ocean. Yeah.
Okay,
but there was very little dissipation.
Okay.
Yeah.
Thank you.
Are there any further questions? Okay, well, thank you very much, Katrine. I think we could all express our appreciation again. And we look forward to hearing your second talk tomorrow.
Thank you.
Thank you.
Very much.
Okay.
Okay.
Bye-bye.